So, a big part of the reason that we talk about water every year is that water is a really excellent example of one particular type of intermolecular force, namely hydrogen bonding. Since the world is full of water, so many reactions occur in water, we sort of focus on that. But the principles that we can apply to water also can be applied to all kinds of different chemicals as well. So that's a little bit what we're going to look at in this piece. We're going to save a lot of the solubility parts to later on when we do the solubility lab. But I'll talk about it a little bit. So intermolecular forces are what we call any sorts of attractive forces between two molecules. So just like an interstate highway goes, through many states, it connects Washington with California. Intermolecular forces connect one water molecule to another water molecule, or one pentane to another pentane, or so on. Intramolecular forces are what we think of as just being bonds. So, covalent bond, for instance. Covalent bonds are much, much, much stronger than the intermolecular forces are. Like even with water, which has one of the strongest type of intermolecular forces, it takes much, much, much less energy to turn it into a gas than it would to actually break the OH bonds in water. So intermolecular forces as a whole are much weaker than the actual bonds that hold the molecules together, which is why when you heat up water, for instance, it becomes steam, water vapor, and not, hydrogen gas, which would be bad. There are some different ways of sort of getting a sense of intermolecular forces within a particular compound. So some of the things that we talk about with water, boiling point and melting point, and then these are the heats of vaporization, which is turning into a gas, fusion, which is melting, and then sublimation, which is going directly from a solid to a gas. So looking at what those numbers are, what those values are, can give us a sense of how strong the intermolecular forces are. Like as we saw with water, the higher in pentane, the higher the boiling point, the stronger the intermolecular forces, the more tightly the molecules were held together within the liquid. So there are 4 different types of intermolecular forces, from strongest down to weakest. We'll talk about each of them. We're going to focus kind of right here, and then a little bit we'll talk about London dispersion as well. Sometimes you might see the term van der Waals forces. If you read in the book, I'm sure you'll find that term. And van der Waals forces is a collective term for those two, for both 3 and 4 together. So just if you see that, that's what it's referring to, dipole-dipole and London dispersion, both together. So the strongest type of intermolecular force is an ion dipole force. We don't talk about this one a ton. I just want to mention it so you've seen it. But this is an attraction between an ion, which has a full charge, and a polar molecule, which has a partial charge. So this is a pretty strong attraction because this ion has lost or gained a full electron. So they have a full charge, whereas the polar molecule has a charged end. So the electrons are just unevenly spread out. One hasn't been totally lost or gained. So this is a strong attraction. The one that you guys are probably most familiar with is hydrogen bonding. We've been talking about it, for days and years, really. This is an attraction that is a super special kind of dipole-dipole interaction, which is the next type, between hydrogen atom in NH, OH, or FH bonds. So hydrogen bonded to FON, FO or N. And what happens is that these atoms are very electronegative. Notice where they are on the periodic table, up in the top right. They're very electronegative, so they keep the electrons around themselves. And so the hydrogens don't have as much electron density around them. And so you get this attraction between the slightly negative O, N, or F and the slightly positive H. It only happens when hydrogen is bonded to O, N, or F. So that's important. Here you can see the way that the electrons would be sort of concentrated and dispersed. So these guys are water, you can see. And then the bigger blob, is formic acid. So this is an oxygen. Since it's double bonded already, it has 2 lone electron pairs. That's a carbon, that's an oxygen, and then the other 2 are H's. So you can see that there's a lot of electron density here. That's red, electron density. And then the hydrogens of the water are slightly positive because there's more electron density on the oxygen side. And so the slightly positive hydrogens are attracted to the more negative oxygen. Down here, the oxygen is attracted to the slightly positive hydrogen because the electrons are away from that hydrogen. So when you're talking about hydrogen bonding, you don't just have to be talking about water to water. You can be talking about any time you have an H bonded to an O or an N or an F. Water is just the most sort of dramatic and the most common example. So the hydrogen bond, as I said, is a special type of dipole-dipole interaction, which is the next one we're going to talk about. So if we look at this is all of the chemicals sort of that you could make as you go across the second group. So hydrogen with carbon, hydrogen with nitrogen, hydrogen with fluorine, hydrogen with oxygen. And as you see, in general, over here, as molar mass increases, so as we go from carbon to silicon to germanium to tin, molar mass is increasing, boiling point increases. As we go from phosphorus to arsenic to antimony, boiling point increases. As we go from sulfur to selenium to tellurium, boiling point increases normally. But when we look at those 3 things that can hydrogen bond, N, F, and O, we get a much higher than expected possible boiling point. And notice water, because of the way that it's going to be arranged, because you have 2 lone pairs of electrons and 2 bonded atoms, you get really nice charge separation. It is the highest of all. So if you look at these masses, hydrogen is 18, HF is 20, and NH3 is 17. So you might expect those to go from highest mass to lowest mass in order, but because water has that really nice charge difference, it is the highest, even though it's not the lowest mass. Okay, so here are what are called dipole-dipole forces. You do need the word dipole twice because you have two dipoles interacting with one another. So a dipole is something with two poles, like a magnet, or in this case, a molecule that has both a positive and a negative pole. So this dipole is interacting with this dipole, dipole-dipole. So dipole-dipole interactions are attractive forces between polar molecules, but because they aren't that special hydrogen bonding situation with N, O, or F, they're not quite as strong as hydrogen bonding. So they're still like attracted, but they're not water strong. So here's a picture. This is of hydrochloric acid. You can see the way the dipole is set up. You have the positive charge on the hydrogen, and most of the electron density is around the chlorine because there's those 3 electron pairs. And so the hydrogen on this hydrochloric is attracted to the lone pairs on the chlorine on this hydrochloric. And so in a beaker, for instance, if you had some liquid or aqueous hydrochloric acid, you'd get this sort of arrangement where the lone pairs of electrons would be aligned or attracted to the positive hydrogens. So very similar to what we saw in hydrogen bonding, just on a much smaller scale, because chlorine, for instance, does not have the electronegativity that fluorine does. So the final type of intermolecular force that we'll talk about is the London dispersion forces. These are forces that are caused because, as you know, electrons are always moving around, and so sometimes temporarily, because of random chance, the electrons on one nonpolar atom will sort of end up temporarily, totally by chance, kind of on one side, setting up a little bit of an electron-dense situation just for a moment, and so that kind of will attract to the next molecule, or atom in this case. So you end up with just this momentary alignment that will hold these molecules together, even though there's no charge disparity, actually. So if you think about the way that dispersion forces are caused just because electrons are moving around, we can think of that as being like how frequently it will happen is how polarizable the molecule is, so how easily that situation can happen. Generally, the more electrons, the more diffuse and the bigger the electron cloud and the more spread out it is, the more possibilities there are for this sort of alignment to happen. Generally speaking, as molar mass increases, dispersion forces also will increase. So for these compounds, which are all carbon compounds with just 4 of the same, for most of them halogens, except for hydrogen, the mass is increasing, and as the mass increases, so does the melting point, because as the mass increases, you're getting more dispersion forces, so they're held a little bit more tightly together. So if we look at these 3 different examples, first we have HBr. If you were to be in this situation on a test, I would strongly encourage you to draw a Lewis structure. So HBr, it's polar because Br has the 3 non-bonded pairs of electrons. 1, 2, 3. So there's much more electron density over here than on the H. So there are dipole-dipole interactions from one HBr to another. And then there are always dispersion forces also. I'm just going to expect you to tell me the strongest interaction, so the dipole-dipole, but do know that there are always dispersion forces happening because electrons are always moving around. CH4 is a tetrahedral molecule, methane, kind of like that. It's all totally symmetrical. Every bonding space is filled with the same element, the hydrogen, and so it's nonpolar. When something's nonpolar, it just has dispersion forces. If you were to compare CH4 to, let's say, CF4, since CF4 is bigger, more massive, and bigger radius-wise, it's going to have stronger dispersion forces than would the methane, the CH4, but both are just dispersion. The last one is SO2. That's a nice little bit tricky Lewis structure that you did in your practice worksheet. Would also have resonance. So it is another polar molecule. There's a lot of sort of interesting arrangements of electrons with the lone pair on the sulfur, as well as the 3 lone pairs here. So there's a lot of disparity happening. So it's definitely a polar molecule. So it has a dipole moment. So it has dipole-dipole interaction. And there are always, as I said, dispersion forces as well. So the way a substance behaves is entirely dependent upon its intermolecular forces. Entirely dependent. This is huge for chemistry. Huge. So these are some things, I'm just going to go through them real quick because we looked at these ideas already in like last year and the year before and the year before. So surface tension, amount of energy to break the surface, basically. Strong intermolecular forces, things with hydrogen bonding, water, and things with dipole-dipole interactions potentially are going to have higher surface tension. Cohesion and adhesion. Cohesion is the molecule sticking to itself. Adhesion is it sticking to other things. Water can stick to itself really well. The stronger the intermolecular forces, the more cohesive a liquid will be. But water also is able to attract to other molecules that are polar, other non-water molecules that are polar. So adhesion and cohesion both for water. Viscosity is something that you might not have talked about before. It's a measure of how a fluid flows, its resistance to flow. So if you think about like maple syrup, for instance, maple syrup has a high viscosity. It doesn't flow very well. Generally speaking, and you guys haven't had as much experience with a lot of these chemicals, but generally speaking, things that have weaker intermolecular forces are going to have like no resistance to flow. So whereas water has a little bit more. It's not like, you don't think of it as being thick like a syrup, but it kind of is a little bit. Here, some of you saw this in class, but this is what happens when water freezes. It sort of locks these hydrogen bonds into place, and so you get these big spaces in the ice crystals. And so that's what makes ice less dense than water. There's this big open structure, whereas in liquid water, these water molecules can kind of all move around and change and bump into each other and whatnot. And so you don't get these big holes. If we were to look at something like lauric acid, as we did in class, it's not going to align in this way. It doesn't have to be attracted to that particular neighbor. It can just sort of, so we'll make it green. It can just sort of pack together. This is terrible drawing. It can just sort of pack together, and then you can get a very dense solid. If any of you remember saturated fats from last year from biology, saturated fats tend to be solid at room temperature, like butter or bacon fat or like beef fat. And the reason that they're solid at room temperature is that they can pack together really, really tightly. And can get very, very dense as opposed to not. So that's what my drawing is representing. So that's intermolecular forces. For the test, you should certainly be able to identify the type of intermolecular forces a particular substance has, especially focusing on hydrogen bonding, dipole-dipole interaction, and London dispersion forces. So, yeah, it'll be fun.